Introduction to Vectors. Lesson 1. Vectors, Column Notation, and Magnitude. Secondary 4G3 Mathematics. If you ask someone for directions and they said, walk 50 meters, then walk 100 meters, then 10 meters, then 5 meters, how would you react? Probably 50 meters? Which way? Do I turn after the first 50 meters? Those numbers only tell you distance, not direction. But when we add arrows showing direction, suddenly everything makes sense. That is exactly what vectors give us, both a size and a direction. By the end of this lesson, you will be able to express vectors as column vectors, find their magnitude, and identify equal, opposite, and zero vectors. Quick review. Here is a Cartesian plane with origin O. The horizontal axis is x, the vertical axis is y. Every point has coordinates x, y. Let us plot a few points. A at 3, 2. B at -1, 4. C at 2, -3. Now recall Pythagoras' theorem. For a right-angled triangle with sides AB and hypotenuse C, C equals the square root of a squared plus b squared. Let us find the distance from O to A. The horizontal side is 3, the vertical side is 2. OA equals the square root of 9 plus 4, which is the square root of 13. A scalar quantity has only magnitude, like mass, volume, or energy. There is just a number. A vector quantity has both magnitude and direction, like velocity, force, and displacement. Notice that vectors have arrows showing direction. A vector can be represented by a directed line segment. It has an initial point where it starts and a terminal point where it ends, with an arrow showing direction. We write vector AB with an arrow on top, or use a bold lowercase letter like a. In handwriting, we add a wavy line underneath called a tilde. Can two vectors at different positions be considered equal? Yes! Vectors care about magnitude and direction, not position. Two vectors with the same length and same direction are equal, even if they start from different points. We can represent vectors using column vector notation. A column vector has two components stacked vertically. The x component tells us the horizontal displacement. Positive means right, negative means left. The y component tells us the vertical displacement. Positive means up, negative means down. Suppose we have point A at the origin, 0, 0, and B at 1, 2. Then vector AB equals the column vector 1, 2. Now suppose E is at 2, 1, and F is at 3, 3. Then vector EF also equals the column vector 1, 2. Notice, vector AB equals vector EF. Even though they start from different points, they have the same column vector. This confirms that vectors with the same magnitude and direction are equal, regardless of position. The magnitude, or modulus, of a vector is its length. For a column vector xy, the magnitude equals the square root of x squared plus y squared. This comes directly from Pythagoras' theorem. For vector AB equals 1, 2. We draw a right triangle. The horizontal side is 1, the vertical side is 2, the vector is the hypotenuse. The magnitude of AB equals the square root of 1 squared plus 2 squared, which is the square root of 5. Now consider vector AB equals 1, 2, shown in blue, and vector CD equals -1, -2, shown in red. Notice, CD equals the negative of AB. Vector CD has the exact same magnitude as vector AB, but points in the opposite direction. We say CD is the negative of AB. In general, if vector A equals xy, then negative a equals negative x negative y. The negative vector has the same magnitude but opposite direction. Watch, if we rotate vector AB by 180 degrees, we get exactly vector CD. What happens if a vector starts and ends at the same point? If we have vector AA, it starts at A and ends at A. There is no displacement and no direction. As a column vector, it is 0, 0. Its magnitude is 0. This is called the zero vector or null vector. Worked example 1. We have A at 3, 4, and B at 7, 4. Part A, write vector A, B as a column vector. Part B, find the magnitude of AB. Solution. AB equals 7 minus 3, 4 minus 4, which gives us the column vector 4, 0. The magnitude of AB equals the square root of 16, which is 4. Worked example 2. Part A, from the origin, go 1 right and 2 down. That gives us the vector 1, negative 2 in blue. Part B, from the origin, go 1 left and 2 up. That gives us negative 1, 2 in red. Part C, they are negatives of each other. Same magnitude, square root of 5, but opposite directions. Worked example 3. P has coordinates 2, 1. Vector PQ equals negative 1, 5. Part A, find the coordinates of Q. Part B, find the magnitude of PQ. Solution. Part A. Q equals P plus vector PQ. That is 2 plus negative 1, comma 1 plus 5. So Q is at 1, 6. Part B. The magnitude of PQ equals the square root of negative 1 squared plus 5 squared, which is the square root of 26. Worked example 4. Vector A equals 5k and the magnitude of A is 13. Find the possible values of k. Solution. The magnitude equals the square root of 25 plus k squared, which equals 13. Squaring both sides, 25 plus k squared equals 169. K squared equals 144. So k equals 12 or k equals negative 12. Here are both vectors on a diagram. 5, 12 pointing upright, and 5, negative 12 pointing downright. Both have magnitude 13. Worked example 5. P has coordinates 103, negative 55. Q has the same coordinates 103, negative 55. Part A, find vector PQ. Part B, what is the special name of this vector? Part C, find its magnitude. Solution. Part A, PQ equals 103 minus 103, negative 55 minus negative 55, which is the column vector 0, 0. Part B, this is the zero vector, also called the null vector. Part C, the magnitude is 0. P and Q are the same point, so there is no displacement. Quiz time. Question 1. Given vector AB equals 3, negative 4, what is the magnitude of AB? Have you got your answer? The answer is B, 5. The magnitude equals the square root of 9 plus 16, which is the square root of 25, which is 5. Common mistakes: option A adds 3 plus 4 instead of using Pythagoras. Option C subtracts. Option D forgets to take the square root. Question 2. If vector A equals 2, negative 3, which of the following is the negative of A? Think carefully. Negate both components. The answer is B, negative 2, 3. Negative A equals the negative of 2, negative 3, which is negative 2, 3. Negate both components. Option A only negated the y component. Option C swapped the components. Option D swapped and negated incorrectly. Remember the directions problem from the start? Walk 50 meters means nothing without a direction. Now you know that a vector gives you both magnitude and direction. Let us summarize. Vectors have both magnitude and direction. Column vectors use XY notation with horizontal and vertical components. Magnitude equals the square root of x squared plus y squared using Pythagoras. Equal vectors have the same magnitude and direction. Negative vectors have the same magnitude but opposite direction. And the zero vector, 0, 0, has zero magnitude and no direction. Next lesson, we will learn how to add and subtract vectors using the triangle.